Over the last few lectures, we have been taking a look at the issue of projective representations of Lie groups, especially in connection with quantum mechanics. In particular, we have seen that a given Lie group will not have intrinsically projective representations if two conditions are satisfied. One, any central charges that are present in the corresponding Lie algebra should be removable by a shift in the generators. And two, the parameter space of the corresponding Lie group should be simply connected. In the last lecture, we had turned specifically to the question of the Poincare group, and we had tried to see whether these conditions hold for the Poincare group or not. In the last lecture, we have actually shown that all central charges in a Poincare algebra can be removed by shifting the generators. So the only question left for us right now is the question of topology. Is the parameter space of the Poincare group simply connected or not? As you all know, the Poincare group is actually a combination of the homogeneous Lorenz group, or just what is called the plane Lorenz group, and the translation group. The translation group is pretty straightforward. The most interesting part of the topology of the Poincare group comes from the Lorenz group, and that is what we are going to take a look at now. We will try to understand the topology of the Lorenz group by relating it to something that is a simpler matrix group, which is the group of all 2x2 complex valued matrices with determinant 1, Sl2c. As we will soon see, the Lorenz group is not identical to Sl2c, but it is very closely related to it. In order to examine the topology of the Poincare group, let us fall back on a construction which may be familiar to many of you from your studies of the rotation group. What we will do is we will start with any given 4 vector, v mu, v0, v1, v2, v3, and from that we will construct a 2x2 Hermitian matrix which we denote by small v. So small v here is capital V mu, sigma mu, where the sigma mu's are the Pauli sigma matrices, at least sigma 1, sigma 2, sigma 3 are the Pauli sigma matrices, and sigma 0 is just the identity. So the matrix small v simply becomes v0 plus v3, v1 minus I v2, v1 plus I v2, v0 minus v3. Now it should take very little effort to convince yourselves that A, this matrix is Hermitian, and B, every Hermitian matrix can be written down in this way. Let me just remind you that the diagonal elements of a Hermitian matrix must be both real, so you can always write them as the sum and difference of two real numbers, and the off-diagonal elements must be complex conjugates of each other, which is why this structure that you see on your screen is the most general possible Hermitian 2x2 matrix. Now, what we will do is take a look at a few properties of this matrix. One of them, a rather obvious one, is that the determinant of this matrix, that of small v, happens to be something which is very familiar to all of us from special theory of relativity. It's nothing but v0 square minus v3 square minus v1 square minus v2 square. In other words, is negative of the norm squared of the 4 vector minus v upper mu, v lower mu. Now, a very important feature is the following. If you were to carry out a transformation where small v changes to a new 2x2 matrix v prime according to the rule lambda v lambda dagger, where lambda is any 2x2 complex valued matrix whatsoever, so it belongs to GL2C. We are going to specialize to the situation where lambda has a non-zero determinant, so it's a non-singular matrix. Now this is going to leave v prime Hermitian. That's very easy to check. All you have to do is take the adjoint of v prime dagger, that will be equal to lambda v lambda daggers adjoint. But as you all know, AB adjoint is B adjoint A adjoint. So using that, this is equal to lambda dagger whole dagger, V dagger, lambda dagger. And lambda dagger whole dagger being lambda, you are back with lambda V lambda dagger, that is V prime stays the same when you calculate its Hermitian adjoint, which of course means that V prime is Hermitian. Since V prime is Hermitian, we can find out 4 real numbers, V prime 0, V prime 1, V prime 2 and V prime 3, such that V prime can be written in the form capital V prime mu sigma mu. And this defines a 4-vector V prime for us. Now, what is very important is that this particular V prime has a norm given by V prime upper mu, V prime lower mu, and that's of course negative of the determinant of V prime, but that's the negative of the determinant of lambda V lambda dagger, and using the fact that the determinant of lambda dagger is conjugate of the determinant of lambda, this translates to negative determinant lambda mod squared times determinant of V. So this ultimately means that the norm of the new 4-vector V prime that we have obtained by this process is actually det lambda mod squared times the norm of the original vector that we started out with. Now, since trace of sigma mu can be easily shown to be twice delta mu nu, it is easy to see that we can directly write down V prime mu in terms of the original components we knew simply by taking the trace of sigma mu times V prime and halving that. And since sigma mu V prime can be written down as sigma mu lambda dagger we knew, we can easily see that V prime mu essentially is V nu times a bunch of coefficients lambda mu nu, which of course depends on lambda, summed over nu of course. And lambda mu nu of lambda can be easily read off from the formula as half of trace of sigma nu lambda dagger. So what is very important here is that this map which goes from capital V, the 4-vector, to a new 4-vector capital V prime is a linear map. The new components are linear combinations of the old components, and it is going to preserve the norm, that is V upper mu, V lower mu is going to be the same as V prime upper mu, V prime lower mu, if we specialize to the situation where mod of det of lambda is 1. So if we only consider those matrices in GL2C whose determinant is a pure phase, this transformation is going to actually preserve the norm and it's linear. So this is then going to be a norm preserving linear transformation, that is, it is going to be a Lorenz transformation. What we have here is the following result. Corresponding to every 2x2 matrix lambda which has a determinant satisfying mod det lambda equals 1, that is a determinant which is a pure phase factor, there exists a corresponding Lorenz transformation, capital lambda of lambda, such that lambda V mu sigma mu lambda dagger is going to give you lambda mu nu of lambda, small lambda, V nu, sigma mu. This of course gives us a rather handy relationship that if you were to linearly combine the sigma 0, sigma 1, sigma 2, sigma 3 matrices using the Lorenz transformation coefficients, lambda mu nu corresponding to small lambda, you are going to get the transformed matrices lambda sigma nu lambda dagger. Not only does this give us a map between the 2x2 matrices with unit phase determinants and Lorenz transformation matrices on the one hand, it actually gives us a map which preserves the group composition properties, in the sense that if you consider two such matrices, lambda and lambda bar, we can easily show that the corresponding transformation which happens because of the product matrix lambda lambda bar induces the product Lorenz transformation. To see this, let's try to calculate lambda lambda bar V mu sigma mu lambda lambda bar dagger using the fact that lambda lambda bar dagger is lambda bar dagger lambda dagger and the associativity of matrix multiplication. We can carry out the lambda bar V mu sigma mu lambda bar dagger transformation first, then carry out the lambda lambda dagger transformation on that. Now, we already know that this particular condition is going to give you lambda mu nu lambda bar v nu sigma mu. That's the inner bracket. But we have to do a lambda dagger on this, and that, remember, acts basically only on the sigma mu because these are just numbers. So the lambda mu nu lambda bar v nu comes out, and you get small lambda sigma mu lambda dagger, which you can always write as lambda rho mu of lambda sigma mu according to what we said a while ago. The only thing you have to be careful about is not to mix up dummy indices. That is why the nu that was there before had to be changed to rho. So what we get ultimately is lambda rho mu small lambda, lambda mu nu small lambda bar, v mu sigma rho. The reason why I have moved this ahead of the lambda mu nu lambda bar is simply that now we have this mu index, which is the column index of the first matrix capital lambda, and this mu index is the row index for the second matrix, which is now in perfect form for matrix multiplication. So this product summed over mu is nothing but the row nth element of the product matrix lambda of lambda, lambda lambda bar. And so this is what we end up with. Now since this is also by definition what capital lambda of lambda lambda bar does to your v, it follows immediately that capital lambda of lambda lambda bar must be capital lambda of lambda times capital lambda of lambda bar. In other words, if you multiply these two 2 by 2 matrices with pure phase determinants together first and then find out the corresponding Lorenz transformation, the result is the same as if you have to calculate the corresponding Lorenz transformation for each one of the individual matrices and then multiply them together. Now you can easily show that the set of all 2 by 2 matrices M which satisfy the condition mod of determinant of M is 1 happen to form a group. And what we have just now shown is that the map small lambda goes to capital lambda of lambda is actually a homomorphism from this group to the Lorenz group. And this will help us go a long way towards understanding the structure of the Lorenz group. However, what we would have loved is that this particular homomorphism, which after all is nothing but a group structure preserving map between two groups, happened to be an isomorphism. That would have been wonderful, because then we would have been able to say that the two groups involved are essentially one and the same, at least as far as the group properties are concerned. In order to qualify as an isomorphism, this homomorphism would have to be 1-to-1. Now this particular map is not 1-to-1. Actually, it's not 1-to-1 by a very, very long shot. Notice that if instead of our matrix lambda, we had chosen a different matrix lambda bar, which is related to lambda by just an extra phase factor e to the I phi times lambda, then the transformation which will be induced on small v by lambda bar v lambda bar dagger, is simply seen to be e to the I phi lambda times v times the adjoint of e to the I phi lambda. And given the fact that the adjoint of e to the I phi lambda is e to the minus I phi times lambda dagger, and e to the minus I phi being a number can simply travel through all the matrices and cancel the e to the plus I phi, we see that lambda bar v lambda bar dagger is exactly the same as lambda v lambda dagger. In other words, the Lorenz transformation which is induced on capital V by lambda is exactly the same as the one which is induced by e to the I phi times lambda. So this particular map is actually infinity to 1, because there are infinitely many 2 by 2 matrices related to each other by this multiplication by a phase factor, which will all lead to exactly the same Lorenz transformation. Now we can cut down on this ambiguity a lot, simply by demanding that instead of considering all 2 by 2 matrices with mod of the determinant equal to 1, we will only focus on 2 by 2 matrices with determinant equal to 1. Now, in doing this, we are not really losing out on any of the Lorenz transformations which we could have otherwise got, for the simple reason that if we start with a particular matrix small lambda, for which det lambda is not 1 but some phase factor, we could simply multiplied by an appropriate phase vector. It's pretty easy to figure out what that is, so that the determinant of the resulting 2 by 2 matrix becomes 1, and we will then use that one instead of our original lambda, simply because, as we have already shown, lambda and lambda times any multiple produces exactly the same effect. So what we are dealing with is a set of all 2 by 2 complex matrices with unit determinant, and this set again can be easily shown to form a group. This group is a very important one and has a special name. It's called Sl2c. L stands simply for linear, the 2 obviously for the 2 by 2 matrices. C simply refers to the fact that this is a set of complex 2 by 2 matrices, and S in the beginning of the name, that stands for special, which is another way of saying that the matrices that we consider all have determinant of +1. So what we have now is a map from any matrix in Sl2c to a Lorenz transformation, and this map preserves the group multiplication structure. Unfortunately, this map too is not 1-to-1, but actually it's a lot closer to being 1-to-1 than the original map that we were talking about. To summarize what we have seen so far, what we have is a map from the group Sl2c to another group, SO31, the group of all Lorenz transformations. And this map carries every 2 by 2 matrix in Sl2c, small lambda, to the Lorenz transformation capital lambda of lambda. And this particular map, capital lambda of lambda, is defined by its matrix elements. Small lambda v mu sigma mu lambda dagger is capital lambda of small lambda, mu nu v nu sigma nu. The important property which this particular map has is that lambda lambda bar maps onto capital lambda of lambda times capital lambda of lambda bar. In other words, what we have is a homomorphism from Sl2c to SO31. Now there are two important questions that we still have to ask. One of them is this map onto, that is all of SO31 covered? And two is this map 1-to-1? Now the second one of these two questions is easiest to answer, so let me answer that first. It's pretty easy to see that there are two multiples of identity in Sl2c. The demand that the determinant of the matrix has to be 1 restricts us to the two possibilities, the 2 by 2 identity matrix and minus I2. Both of these belong to Sl2c. And it's easy to see that if either I2 or minus I2, that is, either one of these 2 by 2 matrices is taken for our lambda, then lambda v mu sigma mu lambda dagger will turn out to be exactly the same as v mu sigma mu. In other words, capital lambda corresponding to plus or minus identity, both will become a 4 by 4 identity matrix, that is, the identity Lorenz transformation. This immediately answers the second question in the negative. This map is not 1-to-1. At least two distinct matrices in Sl2c map onto the identity in SO31. To put this in group theoretical language, the kernel of the homomorphism between Sl2c and the Lorenz group is not trivial. The kernel, by definition, are those elements which map onto the identity of the image group. And by the very basic property of homomorphisms, it is rather obvious that the identity element of the first group must map onto the identity element of the image. So, the kernel of a homomorphism has to be non-empty. It at least has to have the identity of the original group in it. So it's not a surprise that the 2 by 2 identity does map onto I4. But what is important here is that you have more elements than that in the kernel. In addition to I2, you also have minus I2. This is exactly what is expressed by the statement that the kernel is non-trivial. But the question that is really very important here is, are these the only two elements in the kernel, or are there others? That is, other than the obvious choices plus or minus 2 by 2 identity, are there any other matrices in Sl2c which map onto the identity Lorentz transformation? Let us explore that now. A bit of thought will show you that in order that a particular matrix lambda, small lambda, is in the kernel, that is for capital lambda of small lambda to be the identity, we must have the following condition. Small lambda sigma mu small lambda dagger must equal sigma mu for each one of the mu's going from 0, 1, 2 and 3. So our approach would essentially be to see exactly what this condition, or rather these conditions, say about the matrix lambda. But rather than look at sigma 1 and sigma 2, it will be better if we look at sigma 1 plus minus I sigma 2. That is, at the matrices sigma plus or minus given by half of sigma 1 plus minus I sigma 2. These are familiar as raising and lowering matrices in the theory of rotation. They spin half particles. Sigma plus in particular happens to be 0, 1, 0, 0. Let us directly calculate the consequences of lambda sigma plus lambda dagger being sigma plus. So if we start with lambda as any 2 by 2 matrix A, B, C, D, we can of course impose the condition that AD minus BC equals 1 later, but for the time being, let's just start with any 4 complex numbers A, B, C and D. Now this condition, lambda sigma plus lambda dagger equals sigma plus, becomes the matrix ABCD times the matrix 0, 1, 0, 0 times the adjoint matrix A star, C star, B star, D star is equal to 0, 1, 0, 0. Now multiplying the adjoint matrix by 0, 1, 0, 0 on its left simply gives you B star, D star, 0, 0. And multiplying that by lambda directly gives you a 2 by 2 matrix with the 4 elements AB star, AD star, CB star and CD star. Since this has to be equal to sigma plus, this immediately tells us that AD star equals 1, so neither A nor D can be 0. But the other elements of the sigma plus being 0 tells you that AB star, CB star and CD star are all 0. And since neither A nor D is 0, this immediately tells us that B and C must vanish. So our matrix must be of the form A0, 0, D, but because the determinant of our matrix must be 1, this immediately tells you that AD has to be 1, that is D equals A inverse. So we are dealing now with matrices of the form A0, 0, 1 by A. Now let us look at the action of sigma minus on this. Sigma minus, of course, is 0, 0, 1, 0. And now that we know that we have our matrix lambda of the form A0, 0, A inverse, the adjoint simply becomes A star 0, 0, A star inverse. And the product is very easy to carry out. And if you calculate the whole thing, you end up with zeros on the 3 places trivially. So that tells you nothing new. But it tells you that A star by A has to be equal to 1. In other words, the number A, the only parameter left in my matrix now, has to be equal to its conjugate, which means A must be a real number. So using the fact that lambda sigma plus lambda dagger equals sigma plus, we have shown that the matrix has to be of the form A0, 0, 1 by A. And using lambda sigma minus lambda dagger equal to sigma minus after that, we have shown that this quantity A has to be a real parameter. We are still not done because we need to show that the same thing works for all the other sigma matrices involved. Now using sigma 3, what we get is lambda sigma 3 lambda dagger equals sigma 3. And this product, when you carry it out in full, gives you a square 0, 0 minus 1 by a square. And this simply tells you that a square has to be equal to 1. In other words, a has to be plus or minus 1. So we are done. You see that the only possible matrices in Sl2c, which is going to give you lambda sigma mu lambda dagger equals sigma mu for each and every one of the mu's, are actually the matrices you get for a equals plus 1, which is the 2 by 2 identity, and a equal to minus 1, which is nothing but negative of the 2 by 2 identity. So I2 and minus I2 are the only elements in the kernel of our homomorphism. These are the only matrices in Sl2c which map onto the identity Lorentz transformation. Now, if you know any group theory, you would know that the fact that the kernel has two elements really tells you that not only does two distinct elements of Sl2c map onto the identity, the map here is going to be a 2-to-1 map throughout. That is, for every image, every Lorentz transformation that you can get from this map, there are actually two distinct Sl2c matrices. So let us show that directly without invoking the standard group theoretical results which you could have used if you already know about them. So all we are doing is asking under what condition would the image capital lambda of small lambda be exactly equal to capital lambda of small lambda bar. This of course means that lambda sigma mu lambda dagger is lambda bar sigma mu lambda bar dagger for each one of the mu's. But then, if you just take the lambda to the other side, what you are going to get is lambda inverse lambda bar sigma mu lambda inverse lambda bar's dagger. Actually, what you get is lambda dagger inverse, but it's very easy to see that that's exactly the same as lambda inverse lambda bar's dagger is equal to sigma mu. Now, we have already shown that the only two matrices which satisfy lambda sigma mu lambda dagger is sigma mu are the identity and the negative identity. So this tells us that if two matrices small lambda and small lambda bar both map onto the same Lorentz transformation, they must obey lambda inverse lambda bar equals plus minus identity, and hence lambda bar has to be equal to plus or minus lambda. It is rather easy to see that if small lambda is an Sl2c matrix, then so is minus small lambda. And it's also obvious that they give you the same resulting Lorentz transformation. But what we have proven here is that they are the only two which give the same Lorentz transformations. And this is not true about any particular small lambda. For every Sl2c matrix small lambda, the pair small lambda and minus lambda together give rise to the same Lorentz transformation. Let's now return to the previous question. Is this map, the map which takes an Sl2c matrix into a Lorentz transformation, onto? In other words, can I get every Lorentz transformation as a result of such a map? It is very easy to show that the answer is no. After all, if you have lambda sigma nu lambda dagger equals lambda mu nu sigma mu, choosing the special case nu equals 0 immediately gives you lambda sigma 0 lambda dagger is lambda mu 0 corresponding to small lambda times sigma mu. And using the fact that all the sigma matrices are traceless other than the identity, which is sigma 0, it's very easy to see that if you were to actually carry out a trace on both sides, you are going to get twice lambda 0 0. So lambda 0 0 for any small lambda is nothing but half trace of lambda lambda dagger. Remember, sigma 0 is just the identity. So lambda sigma 0 lambda dagger is lambda lambda dagger. Now by simply carrying out the multiplication, it's very easy to show that trace of lambda lambda dagger is nothing but the mod squares of each and every one of its elements summed together, So lambda 0, 0 of lambda is definitely positive. What we have seen earlier though is that a Lorentz transformation can satisfy either lambda 0, 0 larger than or equal to plus 1 or lambda 0, 0 less than equal to minus 1. Now, since we have already shown that our lambda 0, 0 has to be bigger than 0, has to be positive, the only possibility is that it has to be bigger than or equal to plus 1. So, it is not possible to get a Lorentz transformation with lambda 0, 0 less than or equal to minus 1 using this map. The only Lorentz transformations you can get as images from this map are the orthochronous ones. In fact, as we will soon see, the topology of Sl2c will immediately tell you that the only possible Lorentz transformations you can get out of this map are the Lorentz transformations which are connected continuously to the identity, that is the continuous Lorentz transformations. So not just orthochronous, our resulting Lorentz transformations also have to be proper. So we are really dealing with proper orthochronous Lorentz transformations. So this tells you immediately that not all Lorentz transformations can be images, only the proper orthochronous Lorentz transformations can. But that doesn't guarantee us that even if we were to restrict ourselves only to the continuous Lorentz transformations, that is, the proper orthochronous Lorentz transformations, this particular map is going to be onto. We will have to investigate that further. But for the time being, let us first establish this statement that we have made right now, that every element in Sl2c is continuously connected to the identity I2. That is, we need to take a look at the topology of Sl2c. To explore this, we will make use of a standard result from the theory of matrices. And that is the following. Every square matrix lambda can be written uniquely as a product of a unitary matrix and a Hermitian matrix. And if our matrix lambda is non-singular, then the Hermitian matrix also has to be non-singular. A unitary matrix, of course, is non-singular by definition. And this Hermitian matrix can then be written down as an exponential of another Hermitian matrix. So lambda can always be written down as u into e to the power h, where u is a unitary, u dagger u is identity, and h is Hermitian, that is h dagger is the same as h. Note that we are also claiming that we are dealing with Sl2c matrices. So, the determinant of lambda has to be 1. But determinant of u e to the h is determinant of u times determinant of e to the h. And that's determinant of u times e to the power of trace of h. Once again, that's a very standard result in matrix theory, which I'm pretty sure most of you already know. Now, since determinant of a unitary matrix has to be a pure phase, that's a result which follows trivially from the definition u dagger u is equal to identity, just by taking determinants of both sides. So what we have here is e to the power trace of h, which is a purely real number, times a pure phase has to be 1. And this immediately tells us that the only possibility is the determinant of u has to be 1 and e to the power trace of h also has to be 1, which means trace of h has to be 0. In other words, Sl2c essentially is made up of unitary matrices with determinant 1, special unitary matrices, multiplied by exponentials of traceless Hermitian matrices. And since this mapping is unique, that is, for a given lambda there is a unique u and a unique h, the set lambda is in one-to-one correspondence with the set of pairs u, h. So as a space, Sl2c is just the direct product of the space of all the u's, that is all SU2 matrices, and all h's, all traceless Hermitian matrices. Please don't confuse the statement of the direct product with a similar sounding statement about group properties. We are not claiming that Sl2c as a group is a direct product of SU2 and the group of traceless Hermitian matrices. you can easily show that traceless Hermitian matrices do not even form a group under multiplication. What we are saying here is simply that there is a one-to-one correspondence between Sl2c matrices on the one hand and pairs of Su2 and traceless Hermitian matrices on the other. Now, the set of all traceless Hermitian matrices consists of matrices of this particular form. The diagonal elements have to be purely real, of course, but they also have to be negatives of each other. So you have C and minus C. Since the off-diagonal elements have to be conjugates of each other, you can write them to be A minus IB and A plus IB. In other words, all traceless Hermitian matrices are in one-to-one correspondence with triplets of real numbers A, B and C. So the space of all the H's possible, all traceless Hermitian 2x2 matrices, is essentially R3, just the plain three-dimensional space with three real numbers accounting for each and every matrix, and vice versa. But what about the Su2s? Remember, we are dealing with 2x2 unitary matrices, that's what the U's are, but they also have a determinant of 1. Now to check that, this is again something very standard, but if I have not done this before, it's a very interesting result. That if you start with a unitary matrix written as alpha, beta, gamma, delta, this adjoint, of course, is alpha star, gamma star, beta star, delta star. And what about the inverse? Now for a 2x2 matrix, the rule for the inversion is very simple. This works for all 2x2 matrices. You just interchange the diagonal elements, so alpha and delta swap spaces, and change the sign of the off-diagonal elements. Of course, after that, you have to divide by the determinant of U. This is nothing special. It's a standard rule for inversion of matrices. But for 2x2 matrices, it takes a rather special form. And this form is very convenient because 2x2 matrices are things we have to deal with over and over again. In physics at least. Now, since U dagger has to be the same as U inverse, and also since determinant of U is 1, this immediately tells you that delta has to be the same as alpha star and gamma has to be the same as minus beta star. So our matrix U, Su2 matrix, has to have the form alpha beta minus beta star alpha star. So rather than 4 complex parameters, it only depends on 2, alpha and beta. But that's not all. Since we are dealing with Su2 matrices, alpha mod square plus beta mod square, which is the determinant of this matrix, must be equal to 1. So you have one more constraint. Now if you write alpha and beta in terms of the real and imaginary parts, if you write alpha as x plus iy and beta as u plus iv, this condition immediately gives us x square plus y square plus u square plus v square equals 1. This is of course nothing but the equation of a sphere that is embedded in 4 dimensions. This sphere is called S3 simply because it's a 3-dimensional object. Remember our familiar old sphere, the sphere embedded in 3 dimensions is actually S2 because it is described by only 2 independent parameters. Here we are dealing with S3. So from the topological point of view, our group Sl2c is nothing but the same as R3 direct product with S3. And since both R3 and S3 are connected spaces, that is, you can join any 2 points on R3 and any 2 points on S3 respectively, with curves staying entirely within R3 and S3, it follows that Sl2c is also connected, that is, every element of Sl2c is continuously connected to the identity. And that means that any image lambda of this map that we are talking about has to be continuously connected to the identity of the resulting space, that is to I4. This establishes the statement that I have made a while ago that only continuous, that is proper orthochronous Lorenz transformations can be obtained in the image. So SO3, 1 is not the image, but if you restrict it to proper orthochronous set only, and that's indicated here by the upward arrow which tells you the time is flowing in the positive direction, orthochronous, and a plus which tells you that the determinant is plus 1. That's just notation. So the only matrices you can actually get as a result of our map are SO3-1 matrices restricted to proper orthochronous subset. The question is the image all of these? That is, can we get any proper orthogonal Lorentz transformation as a result of this particular map from small lambda to capital lambda? The answer to that happens to be yes. To see this, all you have to realize is that every Lorentz transformation, every continuous Lorentz transformation, can be composed of rotations and Lorentz boosts. In fact, you don't even need all the rotations and all boosts. If you have rotations about any two perpendicular axes, let's say z and y, and a boost about the z-axis, that's enough. So if you can figure out a way of getting rotations about the z-axis and the y-axis, and a boost about the z-axis, using our map, small lambda going to capital lambda or small lambda, then we are in a position to show that every continuous Lorentz transformation can be obtained as the image of some small lambda matrix or the other under this particular map. To see this, let us make a particular choice. Lambda, remember, is of the form u e to the power h. If we choose u to be the identity, and h, remember, is traceless, if we choose it to be diagonal as well, so phi 0, 0, minus phi for a real number phi, then it's easy to see that lambda is simply e to the phi 0, 0, e to the minus phi. Now, if we carry out our map using this particular lambda, that is, if we calculate lambda v mu sigma mu lambda dagger, that is, sandwich our v mu sigma mu matrix between e to the phi 0, 0, e to the minus phi on the left and on the right, because in this case, phi being real, our matrix lambda actually also happens to be Hermitian. So lambda dagger is the same as lambda. We can very easily carry out the multiplication. After all, multiplying by this diagonal matrix from the left multiplies the first row by e to the phi and the second row by e to the minus phi. Multiplying by this diagonal matrix from the right multiplies the first column of the resulting matrix by e to the phi and the second column by e to the minus phi. And putting them all together, you can very easily see that this is what you are going to get. This one, which is in the first row and first column, gets a factor of e to the 2 phi. This one, being in the second row and the second column, gets e to the minus phi from both this one and this one. So get e to the minus 2 phi. These elements, being in the first row, second column and second row, first column, gets e to the phi from one of the two multiplications and e to the minus phi from the other one. So they don't change at all. This is the same as v prime mu sigma mu. So you can immediately read off the v prime components. It's very easy to see that v prime 1 is the same as v1. V prime 2 is the same as v2. So the 1 and 2 components of the vector, capital V, does not change. V prime 0 is nothing but the sum of these two elements, the diagonal elements, divided by 2. And that's cosine hyperbolic 2 phi times v0 plus sine hyperbolic 2 phi times v3. And v prime 3 is nothing but the difference by 2, and that's sine hyperbolic 2 phi v0 plus cos hyperbolic 2 phi v3. A moment's thought will tell you that this is exactly the form that all Lorentz boosts about the z-axis have. The x and y components don't change. The time and the z components mix with each other. And they mix with two coefficients which are gamma and gamma beta. And so you can immediately read off the connection. Tan hyperbolic 2 phi, the ratio between this coefficient and this coefficient, is nothing but our beta. So each and every boost along the z-axis can be obtained by this kind of a map, just by choosing the phi appropriately. What about rotations? Rotations, the story is very similar. If you choose lambda to be e to the I theta 0, 0, e to the minus I theta. So basically here you are choosing H to be the null matrix, e to the H to be just the identity, and you are choosing the unitary matrix to be diagonal. You end up with this calculation, and again it's very easy to see that here what happens is the first row, first column gets e to the I3, e to the minus I3 from both the multiplication, so it does not change. Second row, second column, this diagonal element also doesn't change. Whereas this one actually gets the e to the I theta from the e to the I theta here and then e to the I theta also, so you get e to the I twice theta. And the other diagonal element gets multiplied by e to the minus I twice theta. And now you can easily read off that V0 and V3 do not change. And V1 and V2 change over to V'1 and V'2, which can immediately read off by just adding and subtracting the off-diagonal terms. And this gives us an obvious rotation through an angle 2 theta about the z-axis. So rotations about the z-axis through any arbitrary angle can be obtained this way. I will leave it as an exercise for you to work out rotations through the y-axis. That is really rather obvious. But once you have got these three, rotations about z-axis, rotations about y, and boosts about z, it's easy to see that you can construct any continuous Lorentz transformation out of these. And so, while you cannot get every Lorentz transformation as an image of our mapped small lambda going over to capital lambda, small lambda, we can get every continuous Lorentz transformation this way. So, what we have seen is Sl2c maps onto the continuous Lorentz transformations. But since both small lambda and minus small lambda belonging to Sl2c gives us the same capital lambda, small lambda, we can consider the pairs small lambda minus small lambda together as elements of a set that is actually in one-to-one correspondence with SO31 up plus. Well, not only is this set in one-to-one correspondence in the set theoretical sense, it so happens that if you take these sets together as elements, they also form a group, the so-called quotient group Sl2c by Z2, and it's a very standard result in group theory that the quotient group, when you quotient out the domain of a homomorphism by the kernel of the homomorphism, what you get is the image of the homomorphism. Or what you get is something which is isomorphic to the image of the homomorphism. So even group theoretically, SO31 up plus the continuous Lorentz transformations is the same as the group Sl2c, Z2. Right now we are not really so much interested in the group theoretical feature of this result. We are only interested in the statement that topologically the set of all continuous Lorentz transformations is the same as the set Sl2c by Z2. Not Sl2c directly, but the set of all 2 by 2 unit determinantal complex matrices where we identify a matrix lambda with its own negative. In other words, our SO31 up plus is identical to the set R3 cross S3 by Z2. Note that we have seen earlier that elements of the continuous Lorentz group can be described by 6 parameters, at least 6 infinitesimal parameters when you're talking of elements close to the identity. So close to the identity, the Lorentz group is like R6, but globally its character is different. If you look at the full Lorentz group, what you get is this 6-dimensional manifold R3 cross S3 quotiented by Z2. Now when you go over to continuous Poisson transformations, you add 4 more parameters to the mix. These 4 parameters correspond to the 4 translations and there is no restriction among those parameters. These are just 4 real parameters. That brings in an additional factor of R4. So continuous Poisson group is topologically the same as R4 cross R3 cross S3 slash Z2. Let us now focus on the non-trivial part of this whole issue, the S3 by Z2. Remember, S3 by Z2 is essentially the same as SU2 by Z2. If we focus on any particular SU2 matrix U, a curve on S3 which goes from U to plus U is a loop, obviously, and it's a loop both in S3 and in S3 slash Z2. They are beginning and ending at the same point. On the other hand, if you consider a curve in S3 which goes from U to minus U, now this is actually not a loop in S3, of course, it doesn't start and end at the same point, but in S3 by Z2 what you have done is you have decided to call lambda and minus lambda the same point for any matrix lambda, in particular U and minus U, correspond to the same point in S3 by Z2. So this is also a loop in S3 by Z2. So it's not all of you may be experts in topology. It may be a good idea to explain this a bit through pictures. Unfortunately, I cannot really draw pictures of S3 simply because S3 is a surface which is embodied in 4-dimensional space. However, I can draw images of S2. So, although what we really mean is S3, you will have to make do with images of a sphere in 3D, that is, a 2-dimensional sphere, and its corresponding S2 by Z2 space. Now, consider these two situations. You have a sphere. Of course, this is a 3-dimensional picture which I have drawn on paper. You have to imagine that this is really a solid sphere which has a 2-dimensional surface, and we have a point U on the surface, and we are considering this green curve which is a loop which goes from U to U. This is of course a loop in S2. Of course, I really want to use this to indicate a loop in S3. So you have to imagine that this is really a 4-dimensional space that we are trying to portray. A 3-dimensional surface in a 4-dimensional space. Anyway, that this is a loop should be beyond doubt, and it's a loop in both S3 and S3 by Z2. Or, in the picture, it's a loop in S2 and also in S2 by Z2. Whereas, if you consider this particular loop, well, this curve is not a loop in S2. It goes from a point U to a different point minus U. On the other hand, on S2 by Z2, diametrically opposite points on the sphere are considered to be the same point. So, this curve on S2 by Z2 is actually going from the same starting point to the same final point. So, while this is not a loop in S2, it's a loop in S2 by Z2. I hope this picture makes the thing clear. Now, the very important question is the following. Can we shrink down these loops to a point without breaking the loop? In particular, if we fix a particular beginning point, let's say U in this case, can we shrink down the loop to the point U without breaking the loop ever? Now, of course, that question doesn't even arise in S2 for loops of this kind because this is not even a loop in S2. But we are fully allowed to ask such questions about loops in S2 by Z2. Now, for loops of this kind, it is easy to see that you can actually shrink this down to the point U without ever leaving the surface S2. That is, all you have to do is consider a slightly smaller loop, then a slightly smaller loop again, and ultimately this goes and shrinks down to the point U. Note that I am doing this without breaking the loop, without changing the point U at all, and without ever leaving the surface S2. Of course, each of these curves are also loops in S2 by Z2, and so our beginning loop in S2 by Z2 has shrunk continuously down to a point. Now let us look at loops of this kind. Remember, this is not even a loop in S2, but in S2 by Z2, this is a bona fide loop. So if we keep the initial point the same, that is either this or this, they are essentially the same point, and try to shrink this to a point, then we face a problem because the moment we make this smaller, let's say like this is no longer reaching from U to its antipodal point. That means this curve begins and ends at different points, not only on S2, that it was always doing, but also on S2 by Z2. So what we have managed to do is break the loop, which is not what you are allowed to do. Of course, you could say, well, I will just move the minus U until it goes to plus U along the surface. But when you move this, if you want to keep the thing a loop, you will also have to move the other end. So continuous variation, keeping the loop intact, would actually have changed this point from here to here. So this loop cannot be shrunk down to a point without breaking it. On S2 by Z2 and by extension on S3 by Z2, we actually have two different kinds of loops. Loops which can be shrunk continuously to a point and loops which cannot be shrunk down continuously to a point. So, the conclusion is S3 by Z2 is not simply connected. You have loops on S3 by Z2 which cannot be shrunk down to a point. However, it is important to note that S3 by Z2, while not simply connected, has a connectivity which is not too complicated compared to that. It's actually doubly connected. In other words, any loop on S3 by Z2 which is traversed twice can be shrunk down to a point. That's obvious for loops of the first kind. After all, a loop which is traversed once and can be shrunk down to a point can also be traversed twice, and each one of the individual traversals can be shrunk down to a point. So basically you end up with a doubly traversed loop shrinking down to a point. What is rather non-trivial is the fact that even loops which go from u to minus u on S3 can actually be shrunk down to a point if you traverse it twice. To understand why this is true, let us fall back once again on our picture of S2 by Z2. And here what I have done is drawn a loop which goes from the point u to the point minus u on S2, this green curve, but this really is a loop on S2 by Z2 because it's going from the point u comma minus u to itself. What I'm going to do now is draw the curve once again, but this time I will draw it using the antipodal point. So instead of u, I will take the point minus u. Instead of the next point on the curve, I will take a point here and so on. And I will draw the same curve using the points which were the points on the green curve, but they're antipodal versions. Remember, once again, since u and minus u are identified, so is lambda and minus lambda. This black line that I've drawn here, which actually goes across the real surface of the sphere, is really not a new loop. It is the same loop traversed in exactly the same direction. So that may take some effort to understand, but you have to remember that you are starting the green loop at u. You are starting the black loop at minus u, which is the same point. After a while, as you move along the green loop, you land up here. Similarly, when you move along the dashed black loop, you end up here, which is exactly the same point as this one. Antipodal points on S2, but the same point on S2 by Z2. So now you can think of traversing the original green loop twice as simply taking the green curve and then going back along the black curve. I say going back, but it's really not going back on S2 by Z2. But on S2, it is going back, in the sense that on S2, the green and the black together give you a loop. Now we can of course shrink this loop down to a point on S2 without changing the beginning point, that is staying on U, and without breaking the loop, as well as staying completely on the surface. All I have to do is I have to simply shrink this loop down slowly until it comes to a point. Now when you're doing this, the corresponding loop on S2 by Z2 also shrinks down to a point. Of course, the original loop did visit the beginning point at the middle. That is, starting at u comma minus u, it came back to u comma minus u in the middle of the loop. But when you are shrinking a loop down to a point, you don't really have to worry about what's happening to midpoints. Only restriction is you start and end at the same point throughout and shrink the loop down to a point without breaking it. So I hope this convinces you that traversing the green loop twice, that is essentially traversing the green loop and the dashed black loop, gives you a resulting loop on S2 by Z2 which can be shrunk down to a point. So the upshot of all this is we have two kinds of loops. One which can be smoothly contracted to a point. The other kind cannot be, but if you were to traverse them twice, they can be shrunk down to a point. As I have mentioned in an earlier lecture, the collection of all loops which can be continuously deformed into each other on a manifold form elements of what is called the fundamental group or the first homotopy group of that particular manifold. So what we have essentially shown here is that the fundamental group of our group parameter space S3 by Z2. Of course, we have really shown it for S2 by Z2 by drawing a picture, but you can easily imagine that the same works for S3 by Z2. Has two elements. One is a collection of all loops which can be shrunk down to a point. The other, the collection of all loops which cannot be. Anybody with an elementary idea of group theory knows that there is essentially only one group with two elements. There are many ways of presenting it. In fact, the one that we have talked about is one way of presenting that group. But the simplest way is possibly just take the numbers 1 and minus 1 and form a group under multiplication. Of course, here you have to identify the loops which can be shrunk continuously down to a point to the number 1 and the loops which cannot be to the number minus 1. And so this result that loops which cannot be shrunk to a point when traversed twice gives you a loop which can be shrunk to a point fits exactly with minus 1 times minus 1 is equal to plus 1. Now, in the earlier lecture, I had also said that the moment you have a non-trivial fundamental group for your group parameter space, it is possible that you will get non-trivial projective representations even if you could get rid of the central charges. And the phases of these non-trivial projective representations would furnish a one-dimensional irreducible representation of the corresponding homotopy group. Now that may sound like quite a mouthful, but as I am going to illustrate now, it is pretty easy to understand based on elementary arguments the kind of phases that the intrinsically projective representations of our Poincare group will give, simply because here the first homotopy group is such a simple one. So let us now try to do that. Let us go back to the picture that we used before to talk about projective representations in general, but this time let us use this for the Lorenz group. So here we have a loop in the parameter space of the Lorenz group which goes from the identity to lambda, then on to lambda bar lambda using the composition of the kind that we have already talked about before, and then back along the standard path, which is the orange path, to 1. Now this loop may or may not be contractible because the Lorenz group in general can have non-contractible loops. And this immediately tells us from our analysis of projective transformations that even though we have been able to rid the Poincare algebra of the central charges completely, it may not be true that it does not have projective representations. In particular, U inverse lambda bar lambda, U lambda bar U lambda may end up being a phase factor which is not equal to 1. Of course, it can be equal to 1, but it is possible that it can be a phase factor which is not equal to 1. But if you traverse this loop twice, then the resulting loop is contractible, can be shrunk down to a point. And remember, if you can continuously deform one loop to another, the value at the end, the unitary operator you get at the end by solving the corresponding differential equation, that will not change. And this tells us that the square of this particular combination, U inverse lambda bar lambda, U lambda bar U lambda whole squared, which is what you would get if you were to traverse the same loop twice, has to be the same as the unitary operator you would get if you were to start at identity and go to the identity without going anywhere else. In other words, you must get the identity operator. So now you end up with this possibility that the phase factor, which U inverse lambda bar lambda, U lambda bar U lambda, maybe has to square to 1, and therefore And therefore, the only possible values for the phase factor happens to be plus or minus 1. In other words, u lambda bar u lambda may be either plus u lambda bar lambda, that is, you may have a genuine representation, or it may be minus u lambda bar lambda. So it may be like a representation, but differ from it by a sign. Similarly, for the Poincaré group, u lambda bar a bar times u lambda a can be u lambda bar lambda comma lambda bar a plus a bar, which is the standard representation, but it could also have a representation with a minus sign. So in other words, we can have representations up to a sign for the Poincaré and the Lorenz groups. Note that this has nothing to do with the algebra of the groups. We have already seen that the Lie algebras of these groups can be made central charge free. This result follows simply from the topology of the group concerned. Now come to think about it, this is really not something which is unexpected. After all, we already know representations up to a sign from ordinary quantum mechanics. If we were to carry out a rotation through 2 pi on a quantum system, the overall state of the system may return to its value, or it may return to negative of its value. The latter is a possibility which occurs when you are dealing with odd half integer spins. So behavior of odd half integer spins is simply something which follows from the fact that the rotation group is not simply connected. By the way, it is now time to close a chain in the argument that we had left open earlier when we were talking about massless particles. Remember, when we discussed massless particles and their representations, we introduced this quantity called the helicity. This label sigma which labeled different states. This was the eigenvalue of the operator J3. But whereas for massive particles, this eigenvalue of J3 was confined to be either an integer or an odd half integer, simply from the algebra of the operators involved. For massless particles, the algebra did not come up at all. After all, states with a given helicity sigma did not mix with any other states under continuous Lorenz transformations. So this argument about sigma being an integer or an odd half integer, which arose from the algebra of the angular momentum operators, does not really work for massless particles. Where do we get that from then? The answer simply is this. If we were to rotate through 4 pi, that's essentially traversing a loop in the Poincaré group twice, that loop must be contractible. So a 4 pi rotation must be equivalent to no rotation at all. In other words, if you were to rotate through 4 pi, the state of a system, whatever be the particles that make up the system, must return to its original value. And therefore, the I 4 pi sigma must be plus 1. And that immediately tells you that sigma can either be an integer or a half odd integer. These are the only two possibilities available. This brings us to the conclusion of our discussion on projective representations of Lie groups, where of course our major aim was to look at projective representations, their existence or otherwise, of the Poincaré group. We will wind up our study of this particular chapter of Weinberg's book by looking at the proof of Wigner's theorem, which is one of his appendices. Weinberg actually improves upon Wigner's original proof and gives a rather exhaustive and detailed proof of the theorem. Since this theorem is a very important part of quantum mechanics in general, not just quantum field theory, this is going to occupy us for the next few lectures. So that will be our next part of this lecture course. Bye for now.